So I was doing research on prosthetic arms, and the first thing I noticed is that they are extraordinarily expensive. For $10,000, you can get a prosthetic arm that is literally just a hook. If you want a more complex prosthetic with some ability to make basic gestures like a thumbs up or an OK sign, you can be paying up to $100,000 or more. This is especially a problem for those who do not have enough money to afford such prosthetics, which is most people who need them. This can especially be a problem for children who need prosthetics. Children grow out of prosthetics almost every year. Even if you just went for the hook arm, $10,000 a year is not a cost most households can absorb. That's when I came up with the idea for my next project, building a cheaper prosthetic arm with decent mobility. To do this, I needed a cheap arm and an accurate way to control it. Let's start with the arm. There we go. The design of this arm comes from the InMove project. It has 6 degrees of motion, the 5 fingers, and the wrist. The wrist rotation is done by a servo placed inside the wrist. Pretty simple there. The fingers are a more complicated system. There isn't enough space in the hand to place the high power servos needed to control the fingers. This problem is one that would have faced humans as well, but evolution found a solution. Place the finger muscles in the forearms and use tendons to control them. Each finger has 2 tendons, one that runs through the front of the finger and one that runs through the back. Pulling on the front tendon causes the finger to curl up, and pulling on the back tendon causes the finger to extend. These tendons can be extended from the finger all the way into the forearm. Here's a little demonstration of this arm moving. Making a thumbs up, moving up the thumb, making a fist. Now that we have an arm, we just need an accurate way to control it. To do this, I decided to use Myoelectrics. What are myoelectrics, you might ask? Myoelectric signals are electrical signals that are generated by the muscles when they are active. They can be measured by connecting 2 electrodes to the skin above the muscle and measuring the voltage difference between them. The raw input then needs to be rectified and smoothed to get more meaningful data. There are many circuit boards that can be used for this purpose. I use the MyoAware muscle sensor. I'm currently able to control 2 finger groups, the thumb and the rest of the fingers. Here's a demonstration. This code uses thresholding on the outputs of the muscle sensors to determine whether the fingers should open or close. The thresholds are set during a calibration step in the beginning, where the user has to make certain hand gestures so that the program can understand what they look like in terms of muscle signals. I have tried adding in another finger group, specifically the ring and pinky finger, but this thresholding method becomes less accurate the more freedom of motion there is, and accuracy is more important than mobility. Even if the arm is 90% accurate, which seems good initially, imagine if once every 10 times you pick up a glass, it dropped. That would be terrible. Accuracy is the most important factor here. So where is this going now? I've reached the limit of what thresholding will allow, and beyond this, I have to go to the field of machine learning in order to more accurately control the fingers. Along with this, I will want to achieve proportional control, allowing the fingers to open and close to different extents, not just fully extended or fully curled. Another important part is to be able to control the wrist. Another concern is the arm itself. The arm is physically quite weak since it's made of PLA plastic. If I hit it against a solid object, it could break, very problematic for a prosthetic arm. If you want to create this project for yourself, all the resources are linked in the description. The instructions for building the InMove arm, the locations to place the electrodes on your arm, though that may be different for you, the code that I use to program the arm, and all the electronics that you'll need to buy. Thank you for watching this video.